Good day. I'm going to talk about an impossible program. Quoting Christopher Strachey in 1965, he writes, "Sir, a well-known piece of folklore among programmers holds that it is impossible to write a program which can examine any other program and tell in every case if it will terminate or get into a closed loop when it is run." This was to the editor of the Computer Journal in 1965. He continues, "I have never actually seen a proof of this in print, and though Alan Turing once gave me a verbal proof in a railway carriage on the way to a conference at the NPL in 1953, I unfortunately and promptly forgot the details. This left me with an uneasy feeling that the proof must be long or complicated, but in fact it is so short and simple that it may be of interest to casual readers of a computer journal. The version below uses CPL, but not in any essential way. The CPL language, I will say more about that later." So continuing with Strachey's words in his 1965 letter, "Suppose T of R is a Boolean function taking a routine or program R with no formal or free variables as its arguments, and that for all R, T of R is true if R terminates if run, and that T of R is false if R does not terminate. Consider the routine P defined as follows. Recursive routine P, label L. If T of P go to L, return to the label. If T of P is true, the routine P will loop, and it will only terminate if T of P is false. In each case, T of P has exactly the wrong value, and this contradiction shows that the function T cannot exist. Yours faithfully, Christopher Strachey, Churchill College, Cambridge." That was Strachey's letter in 1965, which I will discuss. But as a teaser, let me ask you the question. Is it correct for Strachey to say that function T cannot exist? Shouldn't he say up front in the top left that T of R is supposedly a Boolean computable function? Just to give two critical remarks at this point, I will say much more later on why I claim that Strachey's proof is flawed. The outline of my talk, well, I just gave a teaser. I will provide an intro for dummies, an intro for smarties, and then I will focus on the core, which is from Turing 36 to Strachey 65, followed by conclusions and a Q&A session. Coming to the intro for dummies, I'll talk about ruler and compass constructions, knot theory, and what I call the Kopet's principle. So let's get started. What can we construct in a finite number of steps with a ruler and a compass? A ruler is also known as a straight edge. It is infinitely long. And here we have a fundamental question. An example is a regular polygon with 17 sides, thanks to a result of Gauss in 1796. But in general, we cannot construct with a ruler and a compass. We cannot double the volume of a cube. We cannot trisect an angle. Due to Wansel in 1837, these are impossibility results. And we cannot construct a square with the same area as a given circle. Essentially due to Lindemann in 1882, because he showed that pi is a transcendental number. For the experts, this will, I think, be sufficient. But the point here is that I'm talking about impossibility results, and Strachey's letter also conveys an impossibility result, but then in computer programming. It took quite some time for mathematicians before they gave up trying to construct these impossible things, and it took quite some time before these impossibility results were proven mathematically. This is a general intro for dummies where I'm trying to convey some general ideas about impossibility results in the adjacent niche of ruler and compass constructions. So it's the 25th of October 2019. That's my voice that you're hearing. My name is Edgar Daylight. The images are from the 22nd, 23rd and 24th of October. And this is my second lecture on the history of computer science, focusing on primarily Strachey and an impossible program. Now, sticking to the introduction, towards a theory of ruler and compass constructions, we have variations that we can start to address once we have some impossibility results proven. Does a compass suffice? The answer is yes. Every point constructible using ruler and compass may also be constructible using compass alone. Does an infinitely long ruler suffice? The answer is no. But a ruler and one circle do suffice. So impossibility results are proven, more theorems are proven about compass and ruler constructions. We have a development from practice to theory, with impossibility results once again, and a hierarchy of techniques, or if we want to call them a hierarchy of languages, or a hierarchy of models of computation. The compass is more powerful than the ruler, so we have a hierarchy. For computer scientists, what will matter for us in the present talk is that a universal Turing machine is more powerful than a linear bounded automaton. This is of course the Chomsky, part of the Chomsky hierarchy that I have just conveyed, and you see an analogy between this result from the Chomsky hierarchy with the ruler and compass constructions. But beware of impossibility results. The ruler and the compass, for example, take into account that the ruler has to be long enough. It has to be infinitely long. The compass's pencil or the lead tip has to be infinitely thin. The ruler and compass do not wear out. We have to have sufficient supply of paper for our ruler and compass constructions. These are idealizations that we should always keep in mind. Likewise for the Turing machine, which is more relevant for us, the Turing machine does not wear out, it makes no mistakes. The tape is supposed to be long enough, and if we have a universal Turing machine, we are assuming we have an infinitely long tape. So these are serious abstractions of real programming technology, and we should never forget this. It's going to be the major theme in the present lecture. I will rely primarily on the 1965 letter of Strachey to the Computer Journal and the article that is my revised article, currently undergoing a second round of review. So, the intro for dummies, I've said something about ruler and compass constructions. Let me now say something about knot theory, relying on Crowell and Fox 1963. See the website for specific references. These authors distinguish between the overhand knot depicted in red and the figure 8 knot depicted in light blue. And again, we're going to discuss very briefly an impossibility result. These authors say that experimenting with a piece of rope will convince anyone that overhand knots and figure 8 knots are different. One cannot be transformed into the other without tying or untying. That's what practice tells us. Then the authors continue. Nevertheless, failure to change the figure 8 knot into the overhand knot by hours of patient twisting is no proof that it can't be done. We shall consider the problem of showing mathematically that these two knots are distinct from one another. At the end of the day, we want to have a mathematical grip on the practical problem of tying and untying knots. But mathematics never proves anything about anything except mathematics, and a piece of rope is a physical object and not a mathematical one. The definitions should define mathematical objects that approximate the physical objects, the physical rope, under consideration as closely as possible. This is a central theme of my critique of Strachey's 1965 letter with regard to the halting problem in computer science. I will rely primarily on my article, which is undergoing a second round of peer review, entitled The Halting Problem and Security's Language Theoretic Approach, Praise and Criticism from a Technical Historian. The topic of security is addressed in my paper, but I will not discuss it in this lecture, just to say that I think it's worthwhile to have a look at my article, because a lot is presented there that I'm not able to discuss here in this rather long lecture, which consists of two parts. You're watching part 1. The second part is available on YouTube as well. For detailed information pertaining to the Crowell and Fox reference and other references, I refer to my website for more details. To recapitulate, there are 4 kinds of objects that I've actually been discussing so far. Finite and infinite objects, mathematical and physical objects. And from a computer science perspective, we'll put the finite state machines in the top left, the Turing machines in the top right corner, and then the laptop in the lower left corner of this table. I will now elaborate on the Kopitz principle, referring to Edward Lee's 2017 book Plato and the Nerd. He says many predictive properties that we assert about systems, such as determinism, timeliness, reliability, are in fact not properties of an implemented system, but rather properties of a model of the system. Typically a mathematical model. We can make definitive statements about models from which we can infer properties of system realizations. The validity of this inference depends on model fidelity. A core notion in my lecture today. Model fidelity is always approximate. So this is very similar to what Crowell and Fox just said with regard to knot theory. It's something I will carry with me in the present lecture. We call the fidelity, and now these are basically my own words, I'm not quoting anybody. We call the fidelity of a mathematical model the degree to which it emulates the engineered artifact, also called the target. In my own words, I claim that Strachey in 1965 ignored the fidelity altogether in his activity of modeling physical computations in which he used computable partial functions as models for executable programs. So this lecture today is highly technical. It is to some extent historical, but I'm also definitely wearing my engineering hat and my hat from computability theory. The undecidable result in hand, not unlike results in adjacent engineering disciplines, holds for the mathematical models of the engineered artifacts, not for the artifacts themselves. Those are some key takeaway messages which I will elaborate on in the coming hour. The outline. I've presented a teaser and an intro for dummies. It's now time for an intro for smarties. I will talk about conflations and I will present terminology in a bit more detail. Conflating the model and the modeled artifact. For example, Dave Parnas on verification says most of the many published proofs of programs in computer science are actually proofs about models of programs. Models that ignore the very properties of digital computers, that cause many of the bugs we are trying to eliminate. Almost everything I present here, when it's my own words that I'm presenting or quotations, almost everything is presented in my article which I mentioned a few moments ago. So the mathematical program is the terminology I'm going to use, is a model, should not be conflated with the executable computer program, that which is modeled. That's the main distinction I want to emphasize over and over, especially when scrutinizing Strachey's 1965 alleged proof of the unsolvability of the halting problem. Perhaps another, more famous example of a conflation is the Y2K or millennium bug. As the 20th century came to a close, more and more stakeholders became aware of the difference between a computer program, which is an executable model in the present scenario that I'm discussing, the difference between a computer program and the dates used in daily discourse, the Model E. So an executable program would have dates like 70, 00 and 00, but in daily discourse it would be about 1970, 1900 and 2000. So we have a discrepancy due to storage limitations. One implication of this discrepancy is that a person born in 1900 turned 0 years old in the year 2000 according to the computer program. So examples of conflations. The Y2K bug was one example. Modern pacemakers is another example. Thousands of pacemakers have been upgraded due to a security vulnerability. Just in my country alone, we're talking about hundreds of thousands in the USA, stakeholders who implicitly believe in a foolproof mapping, that is, stakeholders who conflate the mathematical model of a pacemaker's software with the deployed software itself will put too much weight on the security proofs obtained by researchers. My overarching theme is that the history of science and technology is, besides a history of progress, one of conflations between models and modeled artifacts. I will give 8 more examples to convey this general theme before zooming in on Christopher Strachey's 1965 proof of the unsolvability of the halting problem. First of 8 examples. Linguistics. It is not uncommon to mistake the sentences deduced from a formal grammar for a natural language. For specific references, please have a look at my article. Second example, strong artificial intelligence. One is trained to equate the computation of functions with cognition. A third example, software scholars tend to fuse the categories of Turing machines and stored program computers. This is explained in my own paper in the Communications of the ACM of 2014. And then number 4, engineers mistake a C computer program for system realization. A fifth example comes from DeMilo et al.'s paper some 50 years ago. Computer scientists should not confuse mathematical models with reality, and verification is nothing but a model of believability. See also Donald Mackenzie's book Mechanizing Proof, which is one of my favorite books on the history of formal methods in computer science. Conflations abound. Sixth example. Quine claimed that Russell conflated propositional functions as notations and propositional functions as attributes and relations. Number 7, Russell in turn had applauded Frege for pointing out the common conflation of all and any in deductive reasoning. And 8. Koenig advocated a conceptual divide between set and class to avoid a now famous conflation in set theory. In sum, conflations abound in the intellectual history of computing. The practice of conflating. Let me say something more about that. It is powerful and troubling at the same time. Starting with the powerful aspects, conflating paves the way for mathematical rigor in the science of computer programming, for example, which has led to powerful software analysis tools. Treating computer programs as mathematical objects allows for technical advancements in the software industry. So, of course, mathematics is very important. Second, the drawback. Conflating can lead to ignorance of the model's limited regime of applicability in relation to the Model E. It is not uncommon for computer scientists to confuse the mathematical results of a model in hand with the real-world properties of the modeled artifact. Parnas again. Likewise, ignorance of the modeling activity and too much devotion to the mathematical enterprise can, and I emphasize can, lead to the decision to take the human entirely out of a control loop of, say, a self-driving car, if you like, an automated car, which can easily result in more casualties than when humans and technology form a creative partnership. So this is the general picture about conflations. The tendency to conflate models and modelees is omnipresent in mathematical ideals of engineering. Not only in software engineering or computer science. Engineering is about making the modeled artifact similar to the model and thus correlates knowledge and the making of artifacts. That is why engineering often starts from the assumption of an identification of a model and modelee, and then works its way against the resistance of a material object. Thus, viewing the modelee as identical to the model is both a source of insight and of error. And making this distinction is a matter of testing and a posteriori experience. I thank Erhard Schutbels for conveying this bird's eye view on conflations in science and technology. Now coming to the terminology, I distinguish between mathematical objects and physical objects. I will use the term mathematical programs, and I will of course use the term computable partial functions. These are all mathematical notions. And then physically we have computer programs. They consume energy and take up physical space, and we have laptops as well. So these are the engineered artifacts. Again, they consume energy and take up physical space, which cannot be said of mathematical objects. Now this distinction is very common. In fact, I have already conveyed it in the previous half an hour when discussing the work of our researchers. Is this too simplistic a distinction? Well, let me emphasize that you can make the distinction without subscribing to Platonism, if that's your worry. Second, most historical actors adhere to this distinction. And third, other philosophical positions have yet to be investigated by professional philosophers of computing. So, to the best of my knowledge, this distinction is very common to make, not only with my historical hat, but also with my philosophical hat, if I would have a philosophical hat to begin with. Two more remarks. Computer program versus executing computer program. I'm not going to distinguish between those two. A mathematical program serves as a mathematical model of both a computer program, which is about to be executed, if you like, and it's especially a model of an executing computer program. Then there's also the notion of a program text, which printed on, say, paper or written on the blackboard can represent both a computer program, which is a physical object, or a mathematical program, which is a mathematical object. I'm presenting this terminology for the philosophically inclined viewers. For historians, this is actually not done. For different yet seemingly compatible analysis, a similar analysis, if you like, Ray Turner and his book Computational Artifacts Towards a Philosophy of Computer Science, which appeared in 2018. Turner distinguishes between symbolic programs and abstract mathematical objects. Symbolic programs can be equated to abstract mathematical objects in Turner's book, provided we incorporate the semantics of the containing language in our discourse. I make no such distinction. I simply use the phrase mathematical program. But there's no incompatibility with Turner's account, to the best of my knowledge. Turner also states that programs are not purely mathematical entities. For the former have to be physically manifested. I will simply use the term computer program to refer to the physical components. Unlike me, Turner consistently, in his philosophical book, uses the term technical artifact to unify the symbolic and physical guises of programs. I'm not going to do that. In fact, I'm going to distinguish between the mathematical and the physical parts. Now, more on philosophy, check out these excellent books by Timothy Colburn in 2000, William Rappaport in 2018, and Giuseppe Primiero 2020. That's in a couple of months from now, Oxford University Press. Now, my forthcoming analysis is not philosophically sophisticated, yet it is on a par with the style used by Edgar, who came to the following conclusion: the conflation of representation and reality is a common and significant feature of the whole computer science literature. So if you don't take my word for it, then have a look at Edgar's writings entitled Beyond the Mirror World: Privacy and the Representational Practice of Computing, which appeared in the book entitled Technology and Privacy: The New Landscape, MIT Press, 1997. So this is about database technology and the conflations made in that niche. So coming back to our outline, I presented a teaser, the intro for dummies and smarties, and now I'll focus on the core part from Turing 36 to Strachey 65. Strachey's 1965 letter appeared in January in the Computer Journal with, once more, the following opening sentence: a well-known piece of folklore, which is now central in computer science, by the way, among programmers holds. Folklore, which I call Strachey's halting problem. That it is impossible to write a program which can examine any other program and tell, in every case, if it will terminate or get into a closed loop when it is run. This is something you'll find in every major textbook in computer science today. This modern and now common interpretation of the halting problem is about executable programs. Strachey's narrative stands in stark contrast to the purely mathematical expositions of the halting problem provided by Stephen Kleene, 1952, and Martin Davis, 1958, to give two key examples. For example, Martin Davis, in his 1958 Computability and Unsolvability, provided a far more mathematical account. Davis's proof concerns numerical codes of Turing machines, and his proof relies on Kleene's T predicate, which is defined over the set of natural numbers and used in the context of computable functions. This is purely mathematical. It's totally different from Strachey's 65 account or the accounts you'll find in current day computer science textbooks.